This form of the exponential function is kind of the standard form where a and b are constants and x is the variable. So as soon as you have a variable in the exponent, we consider that an exponential function. So this is the basic form of an exponential function. Um, at this point, you should know that the b kind of determines whether it's an exponential growth or an exponential decay, based on whether b is bigger than 1 or b is between 0 and 1, right? So if b is a number greater than 1, in these examples, kind of like uh, I guess in the example that I was talking about with the uh, 3 to the x, that is a growth function, right? Exponential growth. And then something that would be a decay function is when b is less than 1 but greater than 0. So a number between 0 and 1, which generally we write as fractions or we see as fractions, but they can also be decimals between 0 and 1, right? So if we had like uh, 1/4, and there could be a number in front of it as well, like a 3 times 1/4 to the x power. This 1/4 is the b value, and if the b is between 0 and 1, then the function is a decay function, right? You can think of this b value as kind of the growth factor. That's what it says right here. So if it's bigger than 1, then you're essentially multiplying values by 3 every time. So 3 to the x, if you think about putting a number here, like 7, for example, 3 to the 7, we know what that is. That's 3 times 3 times 3 times 3, right? Or seven of them lined up and multiplied together. So if you multiply things by 3 over and over again, that's going to grow, right? But if you take 1/4 and you line up a bunch of 1/4 multiplied together, that's going to make things smaller. So if I start with 3 and then I multiply by 1/4, it gets smaller. If I multiply by 1/4 again, it gets smaller again. So as we increase this x, this 1/4 is going to compound and make this number get smaller and smaller. That's why it's called a decay function. So the b solely decides whether it's a growth or a decay function. So that's what the b does. The a kind of determines where you cross the. Let me get to the example I want to talk about here. The a kind of determines the vertical intercept of the graph. That's where the exponential growth or decay is going to cross the x-axis. Where's the picture with the graph? There was a nice graph. Oh, maybe not. Oh, sorry. That's in 7.2. We're going to talk about how to graph these in 7.2. Um, right now, we are going to talk about the compound interest formula. So this is used when we're specifically talking about money. Uh, this is the formula down here, and we'll kind of go over the parts of the formula. There's a lot of variables in here. All of the variables essentially are going to be filled in from some kind of information given. So this is an exponential function because we notice that this is a function of time, t, and t is an exponent in this formula. So this is an example of an exponential function because a, which is future value or the account value after 2 years, is a function of t, and t is an exponent. So this is an exponential function. Now, what are some of the pieces in here? Well, p is our starting amount of the account. So that's how much money that you put into the account to begin with. So let's say you go to the bank, you put in $1,000 into the bank, and they tell you, okay, we'll take that money, we'll put it into an account, and it'll earn. Is there an example here? So let's say this person puts $6,000 into the bank, into the investment account, and there will be some kind of interest rate that the bank tells you or has written somewhere, and then there will be a term for how often it's compounded. So compounded monthly is something we're looking for, right? And then we need some kind of time for how long the money is going to stay in there. So these are all pieces of that formula, the compound interest formula, where P is the starting amount, that's how much you put into the account. R is the annual percentage rate as a decimal, so not as a percent. And then N is the weird one, where it's the number of compounding periods in a year. And that is determined by when the question says, or when you see compounded monthly or daily or yearly or weekly. I guess those are, or quarterly. So there's a few up here in this table. These would all follow the word compounded. Right? So if the question says compounded annually or quarterly or monthly or daily, that's what determines our N. And the N is the number of compounding periods in a time period of 1 year. So if an account is compounded daily, so compounded daily means it's going to be compounded every day, which means for over the course of 1 year, that account will be compounded 365 times. Right? That's what N is. N is how many times, essentially how many days are in a year is what the N is in this formula here. It appears in a couple of places. So if it says compounded monthly, then we know that there are 12 months in a year, so it will be compounded 12 times. Right? If it says quarterly, you may have not heard quarterly before, but it comes from the word quarter. And there are 4 quarters in a year, so this is going to be compounded 4 times if the question says quarterly. Finally, if it says annually, that just means once a year, right? So that'll be N of 1. If for some reason a question says compounded weekly, then you need to figure out how many weeks are in a year, which is 52. Let's just squeeze that one in here since we're talking about it. Weekly will be 52 times. Just in case it shows up on your homework assignment or something. Some other terminology I've seen, sometimes they'll do semi-annually, which is kind of like annually, but semi means half, so it's every half a year, so every 6 months, which would be compounded twice a year. So right, if you see semi-annually, that means twice a year. Right, so it'll be one of those few terms for the N. So that's what goes into this formula here. The starting amount goes here. The interest rate goes there in the formula. The number of times it's compounded yearly goes in the N. And then T is how long the money is left in the account. So if you're doing an example like this, let me actually write the formula down here. A of T equals P times 1 plus R divided by N, all raised to the N times T power. So P is the principal amount. So let's identify some of the stuff from the question. This first thing here, $6,000. If we invest $6,000, that is our principal amount. This 6% tells me that the rate R is going to be 0.06. Make sure you convert that to decimals before you do anything with it. Compounded monthly. I know monthly means every month, so how many times a year would that be? That would be N equals 12. And then how much will be in the account? How much will the account be worth in 6 years? That is telling me that T is equal to 6. So T is always in years. So we have all of our values. This is P equals 6,000. And we can plug these into here. So 6,000 times 1 plus... we're just filling in the numbers here. 0.06 for the R, N is 12, so we divide that by 12, and then raised to the N times T, which is 12 times 6, all in the exponent there. Right, and as far as XYZ homework is concerned, you may need to plug that into a calculator. if you're plugging this into a calculator, you may want to do the 12 times 6 first and get a number for that, and then plug that into the calculator as your exponent. If you don't want to do that, you're going to need a parenthesis when you do your exponent. So if you have a calculator with you right now, you may want to practice this. 6,000 times 1 plus 0.06 divided by 12, close that parenthesis, and then raise it to the 12 times 6 power, which ends up being 8,592.27. As far as the exam is concerned, this is where we would leave our answer after we plug in all of our numbers into our formula. Because you don't get to use a calculator, you would be leaving your answer like this. So I guess we can box that and say on exam. That's how we would write our answer for an exam question. But for the homework's sake, for the worksheet, if you want to practice using a calculator to calculate these so that the answer makes sense, that may be useful. The fact that this answer amount of money is more than the starting amount should make sense, because we're putting it in an investment account that is increasing by some interest rate, and we're leaving it in there for 6 years. So after 6 years, the $6,000 becomes $85.92, right? Are there any questions on how to use the formula or get the variable values? Okay, next thing we're going to talk about is exponential functions with a base of e. Now, e is just a number, which this example here, this number is approaching e as we do this more and more. So as you compound more and more often, if a bank account compounds every second, then we have this many seconds in a year, this many seconds in a year, and this formula gets closer and closer to e. The number e is 2.71 something something. That's given here as a rounded number. It's kind of like pi. It goes on forever. It doesn't repeat, and it's a fixed number. It's not a variable. So you need to understand that when you see e as a letter in a formula, that is not something that you're looking for. That's just a fixed number. It's actually a number on your calculator as well. We have this continuous growth or decay formula. These are for accounts or things that grow continuously. So we saw an example where we were doing a compounded monthly kind of growth example in the last problem with the money. If you increase that to daily, hourly, minutely, secondly, this is getting closer and closer to kind of just compounding every moment, right? And if it's compounding every moment, we don't really have a way of counting the number of moments in a year. So as this number gets, or as we compound more and more often, we get closer and closer to kind of an infinity value for n. And when we do that, our rate of growth gets closer and closer to this value e. So essentially, it's an exponential expression for continuous growth or continuous decay, depending on. Now, when we talked about whether an exponential function was growth or decay, we said it totally depended on this b value, right? If the b value was bigger than 1, if b was bigger than 1, then it was growth. If b was between 0 and 1, then it was decay. Now I'm saying that we're fixing the b value as the number e, which generally would mean that this is going to be a growth function. But we're kind of complicating. This is not a basic exponential function. We have a rate here that kind of determines whether or not we're going to be growing or decaying. So these types of formulas, or the compound continuous growth or decay formula, the growth or decay rate depends on the R. If R is positive, then we have a continuous growth. If R is negative, then we have a continuous decay. Essentially, if you want to understand why that's happening, if I have e to a positive number like e squared, that's a growth function, because you can think of it as e squared to the t power, right? And t is the thing that's a variable. So e squared is essentially, how can I show this? E squared, this thing in here, is the old b. That's the b from earlier, right? So that r, or this e to the r power, is kind of like the b from earlier. This thing in here is the b. So if I have e squared, that's exponential growth, because e squared is a number that's bigger than 1, right? But on the other hand, if I have e to the negative 2, and then that's to the t power, this is going to be decay, because e to the negative 2, if you remember what negative exponents do, that's actually 1 over e squared to the t power, and 1 over e squared, this value in the parenthesis here, is between 0 and 1, right? That's a fraction that's smaller than 1. That's 1 over whatever, e is 2.7 something squared, it's 1 over that, which means it is smaller than 1. But you don't have to necessarily think about b every time you think about an exponential function. If you just look at this exponent r here, if that's positive, then you have a growth. If it's negative, you have a decay. In business applications specifically, when we're talking about money, so this is the money growth or decay formula. So money growth / decay formula, just like the last formula that we dealt with, the money, where we said compounded monthly or yearly or daily or quarterly. Here we're looking for the keyword of continuous compounding, right? If they tell you that the account is compounded continuously, we don't have an n for that. Instead, we use the a equals p times e to the rt formula. Everything else is kind of the same. There is no n. The n is missing, so we don't have to look for that. P is the initial value put into the bank. T is how long the money is left in the bank. That's the same. And R is the interest rate given to you. So everything is essentially the same as the P times 1 plus R over N to the NT power formula, except there is no N, and instead we're using E here. Right, so there are essentially less things to worry about in the compounded continuously questions. We have to see a person invested $1,000, which is the P value. P equals 1,000. And we see a nominal 10% rate. That means R is equal to 0.1. And compounded continuously, when I see continuously, I know that I'm going to use A equals P times E to the RT formula. And then it says how much was in the account at the end of the year. So that's telling me that we're doing only 1 year of this account. So my T, my time of money left in the account, is going to be 1. So we plug things into the formula. A is going to equal P, which is 1,000, times E, which is, we leave it as E because that's a number, right? We don't change that. E to the RT power. R is 0.1 times T, which is 1. So we can plug that into our calculator. 1,000 times E to the 0.1 times 1. I guess we don't have to do the times 1, but we get 1,105.17 cents. So this is a dollar amount. I guess we can put units on that, or you can leave your answer like this on the exam. Okay, so there are less things to worry about when the question says compounded continuously. You just have to remember to use this formula for compounded continuously and the last formula for anything else where it says compounded monthly, yearly, quarterly, daily. Cool. So that's all on section 7.1. Are there any questions on that last part of 7.1?
So if we put the continuous growth equation into the calculator, we would put the e to the power of whatever in its own parentheses.
Yeah. Yeah, I would do parentheses around. The calculator kind of does that automatically when you press the. If you have a graphing calculator, it's usually uh, second ln. When you press the second ln, it kind of does e to the some power, and it puts the parentheses for you. So it'll type something like e, and then it'll say caret, and then it'll do parentheses for like putting an exponent on e. It already opens the parenthesis for you, so you just put in the 0.1 times 1 into that parenthesis and close it, and it should work out on the calculator.
Okay, thank you.
Cool. Any other questions before we move on to 7.2? All right, 7.2 is about the graphs. The graphs of exponential growth and decay. I think it's going to make sense to look at this box here at the bottom of page 169. So we can talk about what the graphs look like, where they go through, what the shape is, and what values affect what aspects of the graph. So our basic exponential function, we'll go back to talking about f of x is a times b to the x, where a is greater than 0, b is greater than 0, and b is not 1. The reason why b is not 1 is if b is 1, you get a constant function that just goes horizontally. If b is 1, then you just get f of x equals a, so that would be a horizontal line going through a on the y-axis. But if b is not 1, then you get either a growth or a decay, depending on the value of the b. Remember, if b is bigger than 1, then we have a growth, which means our graph is increasing as we go to the right, so this one is a growth function. And this one is a decay. You see that the function gets smaller and smaller as we go left to right. Right? That's what happens when b is between 0 and 1. Now, some key characteristics are a is very, very important to where the graph crosses the y-axis. So it always crosses at 0, a. Until we start introducing shifts, horizontal or vertical shifts to the graph, we're going to cross at 0, a. So that's a good indication that a is just determining where the graph crosses the y-axis. There's always a horizontal asymptote at y equals 0. The graph will always approach y equals 0 but never cross it. So either going left it approaches the x-axis, or as we go to the right it approaches the x-axis. The domain is all real numbers, so you can go left. This goes up and to the right forever. This goes up to the left forever, and it obviously goes to the right forever as well. So any x value is okay to plug in. But the range is going to be 0 to infinity because the graph is completely above the x-axis in both the growth and the decay formulas, right? It doesn't cross this asymptote at y equals 0. We never get negative y values as outputs. There is no horizontal intercept. It never crosses the x-axis because there's an asymptote there. And then it's increasing to the right if b is bigger than 1, and it's decreasing to the right if b is between 0 and 1. So 2 important points on here that we want to graph every time we do this. And these 2 points are enough to sketch a graph of the exponential growth or decay function. 0 comma a, obviously, that's what we said a determines. A determines where the vertical intercept is. And the other important point is 1 comma a times b. So if you take your a and your b and you multiply them together, and you kind of ignore the x, we get 1 comma a times b as our second point. So those 2 points you should know to graph if you're asked to sketch a graph of an exponential function. Looking at graphs and determining which, so this example gives you 3 functions and says these 3 functions are these 3 functions. And you kind of have to do a little matching, right? You might identify which graph corresponds to each of the functions. This is easy if you know that the graph always crosses at 0 comma a and it goes through 1 comma a times b, right? So if I know that this first function here is f of x equals 1 times 2 to the x, 2 to the x, and then we have another one, g of x is 2 times 2 to the x, and h of x is 5 times 2 to the x, which means these values here, the 1, the 2, and the 5, are my a values. Right? They all have the same b value of 2, which means they'll all have the same general shape. But the a value determines where we cross the y-axis. So this one that crosses the y-axis at 5 is going to be the 5 times 2 to the x. So this here will be h of x. The second graph here where it crosses at 0 comma 2 is obviously going to be g of x, because that's when the a is 2, right here. And then finally the last one will be f of x, because it crosses the y-axis at 0 comma 1. On the next example, we have examples of growth and decay, and we're given 3 functions again, but now the a values are all the same, right? There is no a value here, so it must be a 1. This must be a 1, and this must be a 1. If a is all 1, then we're more concerned with what the b is and how that affects the graph. So if I have f of x equals 1 times 2 to the x, g of x equals 1 times 1/2 to the x, and h of x is 1 times 3 to the x. The only thing changing here in these functions is the b value. So those are the b values. And b is going to determine a couple of things. It's going to determine whether we have a growth or decay function. So we should identify these as growth or decay. The first one here, where b is equal to 2, is going to be a growth function. Right, so it's one of these two that are going up to the right. Those are the growth functions. If b is 1/2, that's certainly between 0 and 1, so this is going to be a decay function. And luckily there's only one of those in the picture, so I can identify it as g of x. Right, and then the last one has a b of 3. That's still greater than 1, which means that is another growth function. So how are we going to decide which one of these growth functions is which one of these growth functions? Well, they're both going to go through 0 comma 1 because the a is 1 on all of these. So actually all 3 graphs are going to go through 0 comma 1 because they go through 0 comma a, right? And the a is 1. The other point that, remember, we talked about that they go through is 1 comma a times b. So if we multiply the a and the b together in either of these, we should be able to tell which one is which. So if I multiply the a and the b together, that's 1 times 2 is 2. So this function should go through 1 comma 2. And this function down here should go through 1 comma 3, because 1 times 3, a times b is 3. Right, so 1 comma 2. The one that goes through 1 comma 2 is this one here. This is 1 comma 2. So it means this one must be f of x, and the one that goes through 1 comma 3 must be h of x. All right, so we can identify using the idea of growth or decay as kind of like a first check of which way is the graph supposed to be oriented. Whether it's going up, those are growth, or it's going down, that's a decay. And then after that, you can use your points for 0 comma a or 1 comma a times b. So we have two kind of ideal points that we can look at to determine which one is which. Cool. And then you may be asked to graph some of these on the homework or the exam or the worksheet that I posted on Canvas. If you're asked to graph, then these 2 points are enough for a sketch of a graph. I would just plot those 2 points for any given exponential function, and then knowing whether it's growth or decay kind of tells you which direction you're going in. I mean, these points will also tell you which direction you're going in, but knowing that the b determines growth or decay tells you that your graph is either increasing to the right or decreasing and getting smaller as you go to the right.